Our last speaker this morning will be Joel Smith, speaking on modeling linkage and mutation to estimate the timing of adaptation. The last speaker of our session. Please, Joel.
Thanks. So I'm Joel Smith. I'm a third-year grad student at University of Chicago, and I'm going to present some work that I started a while ago, but that I'm excited to present now in a somewhat completed form. So I want to start with the hard sweep model, which many people here should be somewhat familiar with. So here we have a mutation that arises in a population at some time in the past, and then because that mutation confers some selective benefit, it moves through the population faster than the rate at which recombination and mutation can replenish variation at that locus. So what you end up with is a locus here with the allele fixed at this site and linked variation also fixed as well. But over time, this signature decays at a constant rate because of recombination and mutation. So this is a really useful signature, and it's one of the best ways we know of to identify loci that are under selection. But usually the inference stops there. So in fact, there's actually a lot more information, or I think there's a lot more information associated with these sweeps that we can use to infer important parameters about the adaptive history. So in particular, I want to know if we can estimate the timing of selection for this beneficial mutation. And this is a really interesting question intrinsically, but there are a few others that are sort of associated with this that we would also like to know. One is, what is the relative timing of positive selection events for a given species? Can we correlate the timing of adaptation with known environmental changes in history? Was this selection on a de novo mutation or standing variation? What is the population of origin for this mutation? What was the strength of selection? So previous approaches have tried to do this, but they rely on a simulation or rejection sampling based work, oftentimes in an approximate Bayesian computation approach, where the basic gist is that you choose a parameter value, simulate data under that parameter. If that data matches your observed data pretty well, then you accept that parameter value. And you do this over and over and over again until you get some distribution of parameter values that are consistent with your data. And for humans, this has been done to look at lactase persistence in Africa and Europe at the lactase locus. And you get mean estimates of 8,000 years in Africa, 4,000 years in Europe. But the problem is that the confidence intervals are huge, from 1,000 years ago up to 23,000 years ago. For skin pigmentation in Asia and Europe, at the KIT-LG locus, we have 30,000 years ago, plus or minus, up to 77,000, and as recent as 5,000. So what this model I'm going to present is going to try to do is provide more narrow confidence intervals for these events. So to be a little more explicit about what exactly I'm estimating, this is a cartoon showing a genealogy at a locus where a mutation occurred sometime in the past that began increasing in frequency due to its selective benefit. The genealogy of this locus, moving backwards in time, is forced to coalesce rapidly as the frequency of the allele drops moving backwards in time. So this is similar to what you would expect under a population bottleneck, except this is just at a single locus, potentially in a population that's at constant size. So to help us build some intuition for how we can do this using derived mutations, this is what's known as the Thompson estimator. And basically, it's a weighted average of the number of mutations back to this common ancestor, where yi is the number of mutations on lineage I, L is the length of haplotype I, and mu is the mutation rate. And so, assuming this star genealogy, we can get a mean estimate using these mutations. Similarly, we can use haplotype lengths. So here we have a plot where we have position along a chromosome or a sequence of data for many individuals. And the selected locus is right here in the middle. And we can model this haplotype length as being exponentially distributed with rate equal to the recombination rate times the time of the common ancestor. And the expected value for an exponential is just the reciprocal of the rate parameter here. And so if we can just solve for t, we can get an estimate using these expected lengths. So I can simulate data under this simplified model, and it oftentimes looks very pretty. And these lengths are all independent, and these green mutations are arising on this haplotype in a Poisson process. And over time, you can see that these lengths decrease in size, and also the density of these mutations is increasing on the haplotype. So this is very pretty, and is sort of one of the independence assumption is something that we're going to use, but we'd like to know if that's actually like a reasonable assumption to make. And because in reality, the haplotypes probably look something more like this. So you can see there's some recombination events here that are definitely non-independent. In addition, we have haplotypes that have recombined off and are still floating around in the population, so those could recombine back onto the selected haplotype and make something look longer. So if what we can do is simulate many of these populations, which were simulated conditioned on an allele frequency trajectory under a coalescent framework. And in those cases, we know what the time to the common ancestor is. And using the relation I just showed you, we can see what the expected length is given that time to the common ancestor, and see how well it matches our observed haplotype lengths. And you can see it actually does pretty well, which is interesting, and I don't know exactly why, but that requires a little bit more investigation, I guess, if you want to. So now I'm going to present our approach in more detail. The first thing we need is individuals that have the selected allele, as well as individuals that don't have the selected allele. So we would expect this kind of scenario during a partial sweep, potentially, or also during a local sweep where you have two populations that have diverged, where one has experienced the selective pressure and the other has not. This is a cartoon of the haplotype copying model that we're going to use. And it's a hidden Markov model where basically we have a sequence of data and we're trying to infer what the hidden state is at each locus. In our case, the hidden state is a switch from the ancestral haplotype onto the background haplotypes here that don't have the selected allele. So this is what the likelihood looks like. We have our sample of individuals that have the selected allele, our time to the common ancestor, the ancestral haplotype, and our sample of reference haplotypes. This product is where we're invoking the star genealogy assumption, where each individual is independent from every other. The likelihood for each individual xi is shown here, where we don't actually know where the recombination event off of the ancestral haplotype is, which is this probability that W equals W. So we could potentially try to infer that, but instead what we're going to do is treat that as an uncertain random variable and integrate across all possible recombination events. So here's just another representation of the slide I just showed you, except we have a cartoon here. And I'm dividing the likelihood term up into two different components. One is this alpha term, which is the fraction of the site that's on the selected haplotype. And here's the beta component, which is the fraction of the locus that's off of the selected haplotype. And I'm not going to go into any more details about the likelihood right now, but all I want to say is that the probability that we observe a mutation at this site depends both on the time to the common ancestor as well as what we think the ancestral haplotype is at that locus. So as a proof of concept, I'm first going to show you an analysis on simulated data when we know what the ancestral haplotype is. And it looks really good, not too surprisingly. The important thing to note is that we can get independent estimates using the mutation TMRCA versus the recombination TMRCA. And we can also use them jointly in this with these green dots. And you can see that it's actually has much lower variance than either one of those would have independently, and so that's a really good thing. In reality, we don't know what the ancestral haplotype is. So instead of using maximum likelihood, what we have to use is Markov chain Monte Carlo to estimate the ancestral haplotype jointly. So to initialize our MCMC, we draw a value for t that's randomly drawn. And the ancestral haplotype is initialized using the consensus allele among advantageous allele carriers. So if you're familiar with extended haplotype homozygosity or other similar approaches to detect selective sweeps, it's a very similar approach as you would use for those. And proposals to T are generated by adding a normally distributed random variable centered at 0, and proposals to the ancestral haplotype are made by randomly selecting sites and switching to the alternative allele. These are mean posteriors and 95% intervals for estimates on simulated data that I simulated under the coalescent. And you can see it looks pretty good. If you're interested in seeing the trace files for the MCMCs, I'd be happy to show you, but they also look pretty good. They're really good. Now I'm going to show you real data. So I used the 1,000 genomes data, which is a publicly available data set for humans. And at this point, it's well over 1,000 genomes. It's somewhere between 3,000 and 4,000. And sampled from around 20 populations around the world. I'm going to start dropping the timing for selection on this timeline, but to sort of give you an anchor point, I've drawn this arrow for the migration out of Africa timing. And just so you know, current estimates for the migration out of Africa are as early as 120,000 years ago and as recent as 80,000 years ago. So just keep that uncertainty in mind as I start showing you these plots. So first I did the KIT LG locus in non-Africans, which is found outside of Africa and is associated with skin pigmentation. The reason this is multimodal is because this is actually a bunch of different posterior distributions from different populations in there, and they all happen to cluster in the same place between 20 and 30,000 years ago. OCA2 is another skin pigmentation allele only found in East Asians, and it's nested right in the middle of the KIT LG selection time. So previous estimates for TERP1, which is a skin pigmentation allele private to Europeans, or only found at high frequency in Europeans, using the HapMap data, which is genotype data, so it's not sequencing data and only tagging common variants, gives us a really recent estimate for when the timing of selection happened at this locus. So it was thought that after the migration out of Africa, there was a divergence time between East Asians and Europeans, at which time they had some independent evolution of skin pigmentation in these different populations. So when I use the 1,000 genomes data with my model, it actually makes this time the timing of selection at this locus much earlier, potentially before the Europe and Asia split. The other thing to note is sort of the spread of the timing of selection across these populations. So they're oftentimes separated by tens and 20,000s of years, starting all the way back 90,000 years ago. So TSI and IBS are the Iberian Peninsula and Italy. Great Britain is GBR, CEU is Western Europeans, and Finn is Finland. And so the other thing you notice is it actually is also moving from a south to north gradient. And so, I mean, there's a variety of interpretations you could draw from that. The next locus I looked at was EDAR in East Asians. And this is associated with hair, or thicker hair and dentition, and is also clustering more closely with skin pigmentation alleles, you know, as early as 15,000 years ago. And then we have the lactase persistence allele in Europeans, which is the strongest and most recent signal, and this also confirms other data sets. It also coincides nicely with what we know about pastoralism in Northern Europe in the archaeological record. We can zoom in on this data and see what the timing of selection is within each one of these populations, and there aren't any really clear patterns. We have Western Europe being the oldest, then Finland and Great Britain. Italy and the Iberian Peninsula happen to share the same time as Finland, which is interesting. So to give you, you know, an overview, we've Developed a full likelihood-based method to estimate the age of a selective sweep. Future extensions may include the inference of multiple ancestral types, as well as the geographic trajectory. Increased sampling and data quality continue to improve our understanding of the adaptive history of natural populations. With that, I just want to thank my mentors and my friends who helped me out. Thanks.
So as we've gone into the end of this session,